Evaluation metrics are the tools used to measure how well an AI model performs. This video explains why metrics matter, what they actually measure, and how choosing the wrong metric can lead to misleading conclusions about model quality, usefulness, and real-world impact. A model's output alone does not tell us whether it is good or bad. Evaluation provides a structured way to compare predictions against reality. Metrics translate performance into numbers that allow models to be tested, compared, and improved systematically. Metrics act as feedback signals. They guide training decisions, model selection, and deployment choices. Without metrics, machine learning would rely on intuition rather than evidence, making systems unreliable and difficult to trust. Different tasks require different metrics. A metric that works well for one problem may be misleading for another. Understanding evaluation metrics helps avoid incorrect assumptions about what a model is actually optimizing for. Evaluation always compares predictions to ground truth. Ground truth represents the best available reference labels, typically provided by humans or trusted systems. Metrics quantify how closely predictions align with these reference outcomes. The simplest evaluation metric is accuracy. Accuracy measures the proportion of correct predictions out of all predictions made. It provides a high-level view of performance, but can be misleading in many real-world scenarios. Accuracy is calculated by dividing the number of correct predictions by the total number of predictions. If a model predicts correctly most of the time, accuracy will appear high, even if important errors are being ignored. Accuracy works best when classes are balanced. In balanced datasets, each outcome appears roughly equally often. In these cases, accuracy provides a reasonable summary of overall performance. However, many real-world datasets are imbalanced. One class may be much more frequent than others. In such cases, a model can achieve high accuracy while failing to detect rare but important events. For example, in fraud detection, fraudulent transactions are rare. A model that always predicts not fraud may achieve high accuracy while being useless. This limitation motivates the use of additional metrics. To address this, precision and recall are introduced. These metrics focus on specific types of errors rather than overall correctness. They are especially important in tasks where false positives or false negatives carry different costs. Precision measures how many predicted positives are actually correct. It answers the question, when the model predicts a positive outcome, how often is it right? High precision means the model makes few false positive errors. This is important in scenarios where incorrect positive predictions are costly, such as spam filtering or medical diagnosis. Recall measures how many actual positives the model successfully identifies. It answers the question, out of all true positive cases, how many did the model detect? High recall means the model misses few positive cases. This is critical in safety-related domains, such as disease screening or fraud detection, where missing a true case can have serious consequences. Precision and recall often trade off against each other. Improving one can reduce the other. Increasing recall may increase false positives, while increasing precision may reduce the number of detected positives. Choosing between precision and recall depends on the problem context. The metric that matters most reflects which type of error is more harmful in the real-world application. To balance precision and recall, the F1 score is commonly used. The F1 score combines both metrics into a single value that reflects their harmonic mean. The harmonic mean penalizes extreme values. A model with very high precision but very low recall will receive a low F1 score, and vice versa. This encourages balanced performance. The F1 score is particularly useful when classes are imbalanced, and both false positives and false negatives matter. It provides a more nuanced assessment than accuracy alone. Beyond classification, other tasks require different metrics. Regression models, for example, predict continuous values rather than discrete categories. Accuracy and precision are not suitable in these cases. Common regression metrics include mean absolute error and mean squared error. These metrics measure how far predictions deviate from actual values, focusing on prediction error magnitude. Mean absolute error measures the average absolute difference between predicted and true values. It treats all errors equally and is easy to interpret. Mean squared error squares errors before averaging, which penalizes large errors more heavily. This makes it sensitive to outliers and useful when large deviations are especially undesirable. Metrics do not only evaluate models, they shape model behavior. During training, models optimize loss functions that are closely related to evaluation metrics. The choice of metric influences what the model learns. Optimizing the wrong metric can lead to unintended outcomes. A model may perform well numerically while failing to meet real-world needs. This disconnect is a common source of deployment failure. Metrics must align with business goals, ethical considerations, and operational constraints. Technical performance alone is not sufficient to judge model success. Evaluation should be continuous, not one time. Model performance can change as data distributions shift, user behavior evolves, or environments change over time. Monitoring metrics after deployment helps detect degradation, bias, or unexpected behavior. Evaluation is therefore a core part of responsible AI lifecycle management. Metrics are also used to compare different models. Benchmarking allows teams to select models that perform best under consistent evaluation conditions. However, metrics can be gamed. When teams focus narrowly on a single metric, models may exploit shortcuts that improve scores without improving true performance. This phenomenon is known as metric overfitting. The model becomes optimized for the evaluation measure rather than for the underlying task objective. To mitigate this, multiple metrics are often used together. Viewing performance through several lenses provides a more robust understanding of model behavior. Human judgment remains essential in interpreting metrics. Numbers alone do not capture social impact, fairness, or user experience. Evaluation metrics should be transparent and documented. Stakeholders need to understand what metrics mean and what their limitations are. In regulated domains, metrics support accountability. They provide evidence for performance claims and help demonstrate compliance with standards and policies. Metrics also influence trust. Clear, appropriate evaluation builds confidence among users, decision makers, and affected communities. Choosing metrics requires domain knowledge. What counts as a serious error in one field may be acceptable in another. Context always matters. No single metric captures all aspects of performance. Effective evaluation balances simplicity, interpretability, and relevance to real-world outcomes. Evaluation metrics are not neutral. They encode priorities and values. Deciding what to measure implicitly decides what matters. As AI systems become more widespread, metric selection becomes a governance issue, not just a technical one. Understanding metrics enables better communication between technical teams and non-technical stakeholders. Metrics help diagnose failure modes. By examining where performance drops, teams can identify weaknesses and target improvements. Evaluation also supports iteration. Metrics guide experimentation, helping teams refine models systematically rather than randomly. Poor evaluation can hide harm. Models may appear successful while producing biased or unsafe outcomes for certain groups. Responsible AI requires aligning metrics with fairness, safety, and long-term impact, not just short-term accuracy. Metrics should evolve as systems evolve. Evaluation frameworks must adapt to new data, new risks, and new deployment contexts. The key takeaway is that metrics are tools, not truths. They support judgment but do not replace it. Understanding evaluation metrics empowers practitioners to build, deploy, and monitor AI systems more responsibly and effectively. Next, we will move beyond evaluation to examine how models fail in practice and why understanding limitations is as important as measuring performance.